Thanks. Hey guys, I want to thank you all for coming tonight, and thank you so much to Square for hosting this event. My name is Fangjin, and I am a software engineer at a San Francisco startup called Metamarkets. And tonight I wanted to talk to you guys about Druid, which is an open source distributed data store that I work on. So some of the things we'll cover tonight, I'll show a brief demo of a product that's been built on top of Druid to motivate some of the problems that Druid has been designed to solve. I'll talk about the history and the motivation of why we decided to build our own data store, and then subsequently open source it. And then finally, I'll talk a little bit high level of the architecture of Druid, where I'll show off some pictures with arrows, and hopefully you guys can figure out what's going on. So to really understand what the problems that Druid is meant to solve, I have a very brief demo of actually a dashboard that's been built on top of Druid. And this dashboard is meant to showcase edits as they're occurring on Wikipedia. So hopefully everyone here is pretty familiar with Wikipedia. There's a lot of pages about a lot of different cool content, and basically anyone can go on and make an edit. What happens when someone makes an edit is basically an event gets created, and this event gets sent to an IRC channel that we then scrape and dump into our data store. So this event has a couple of different parameters. It has a timestamp indicating when the event occurs. It has a set of attributes or dimensions about the edit. For example, the name of the page that's being edited, or the language of the page, or like information about who's doing the edit, like the user information. There's also metrics associated with this event. For example, the number of characters that were added or the number of characters that were deleted. So what this dashboard is meant to showcase is basically you can see as they're trending across time. And you can filter on different attributes to see how those edits are changing. So for example, I can filter on country, United States. And I can filter on, or city, or San Francisco. San Francisco, and then we can see that Georgiism is getting a lot of edits this week. I have no idea what that is. And also, California Culinary Academy has been getting some love this week, which is kind of cool. And you can do things like you can compare how different pages are being edited across time. You can zoom in on different time granularities, and you can really explore your data. You can drag like this graph back and forth and explore how your data is changing for different granularities of time. Okay, so all the queries that you see right now are being issued effectively live to our data store called Druid. And if I drag this graph to the current time, the ingestion should be relatively live as well. So we should, if people start making edits like right now, we should actually be able to see them in this dashboard. OK. So the dashboard I just demoed is really a way to explore data, explore specifically time series or transactional data. In this particular case, it was data for Wikipedia. I work for a company called Metamarkets, and Metamarkets is not a social media company. We actually primarily deal with transactional or event streams that are specific to the ad tech space. However, the problems that we mean to solve with this dashboard and the problems that we mean to solve with Druid are basically three main things. One, we want to solve the data exploration problem. So we want to be able to arbitrarily slice and dice data and drill into that data effectively without any restrictions. The second problem that we want to solve is around data ingestion. So if some event occurs, for example, if someone edits something on Wikipedia, we want to be able to almost immediately ingest that event and then also make that event explorable. Finally, we are a software as a service company. So we are a cloud-hosted solution, and its availability is very important to us. Our systems need to be constantly up and be able to withstand all sorts of different failures that can occur without going down and without taking any downtime. So Metamarkets was founded late, mid-2010-ish. And we kind of knew in the early days that we wanted to build this like dashboard that we want to be able to deliver to our clients and have them be able to explore data. What we didn't know was the data engine that we could use to power our dashboard. So in the early days of the company, there were actually a bunch of different solutions that we tried. One of the first things that we tried was a relational database management system. If you're familiar with relational databases, their benefits are extremely well documented. MySQL and Postgres, they're extremely popular in all sorts of different industries. So we actually ended up trying Postgres. And the setup that we used is pretty common in the data warehousing space. If you're not familiar with data warehousing, don't worry. The basic setup is you have like a star schema, you have your fact table in the center, you have your dimension tables on the side. You have your aggregate tables, and you have query caches to try and improve query latency. What we found with using Postgres was basically queries that were cached. They were generally pretty fast. Queries that went against aggregate tables, they were fast to acceptable. But the real problem came with queries that hit the raw data. And anytime we needed to hit the base fact table and scan the raw data, those query latencies were pretty much unacceptable to us. For our dashboard, interactivity was very important. So we wanted users to be able to click and get an interactive experience and see their data like updating without having to wait. So what we found with benchmarking Postgres was basically the scan rate was about 5.5 million rows per second per core. A query over about 1 week of data took about 5 seconds, which is like OK. The main problem is with queries that exceeded time ranges longer than that, and especially with concurrent queries. So a page load with 20 queries over about a week of data took an order of minutes, and that was a really uncomfortable, not very interactive experience. Every time you actually use our dashboard, so in that Wikipedia dashboard you saw earlier, every time you click on something, there's somewhere between like 20 and 30 different concurrent queries that go to our data store. So we tried Postgres. We didn't really like it. It didn't really work out very well for us. So we started looking at other solutions to this problem. And the time frame I'm kind of talking about here is about early 2011-ish. And in early 2011-ish, NoSQL key value stores were extremely common. And within this space, you have data stores such as like Cassandra. You have like your HBase. You have all the big data clones, big table clones, sorry, and all the Dynamo clones. And they were pretty hot. So we said, hey, let's give HBase a shot. So because HBase is a key value store, there were certain limitations as to how you could use it for data exploration. OK, basically, let's say you had a very simple table, a very simple data set here. OK, there's a timestamp dimension, there's a gender dimension, there's an age dimension, and there's like a revenue metric. So if I wanted to know how much money did I make when the timestamp is equal to 1, the value that you end up having to store in a system like HBase is basically your key is equal to 1. And then your revenue is the sum of these three. Similarly, if you wanted to know how much money did I make when timestamp is equal to 1 and gender is equal to female, and then the entry you end up storing is, the key is timestamp 1, gender female. The revenue is the sum of the last 2 rows here. So to be able to arbitrarily explore this data set really without bounds, you end up generating a lot of things that you have to store in your NoSQL store. And it's very easy to see that as your data volume increases, as your data complexity increases, the number of entries you end up storing kind of scales exponentially. So what we found with using HBase was queries were pretty fast because you're basically just doing like a lookup into a map. The solution tended to be somewhat inflexible. Basically, if something wasn't like pre-computed or something wasn't pre-aggregated, then you couldn't query it. Like if entry didn't exist in your HBase data store, you couldn't query it. Another problem that we found was data was not being continuously updated. So because we deal with like event streams and we deal with transactional data, we see events constantly come in. And when those events came in, we could not use a system like HBase to explore them. And then finally, the biggest problem of all for us was the processing time, the pre-computation time to figure out effectively every permutation of combination of dimension combinations that you could possibly have, your entire query set. So when you have like many dimensions in your data, it's very easy for there to be an exponential increase in the number of entries you have to end up storing. We saw this problem with HBase, but we didn't give up right away. What we actually tried to do was we basically tried to limit the possible queries that a user can make. So you try and limit your dimensional permutation expansion set. Within academia, there's this concept called iceberg cubing. And iceberg cubing is similar to what it sounds. When you have an iceberg, you can think of most of the volume of the iceberg being hidden under the water, and you have like a very small amount that's like the tip. Similarly, when dealing with pre-computation of data, what you try and do is you don't try and pre-compute out every single possible query that the user can make. You kind of try and limit the queries that they can make, and you try and restrict the query set. But even using this method, we didn't get very good results. And what we found was on a data set that was 500,000 records, the processing time with 11 dimensions, when we limited our dimensional explosion to about 5 dimensions, took about 4.5 hours on a 15-node Hadoop cluster. Similarly, when that data set increased to 14 dimensions, and we're still limiting our query set, we're still limiting our dimensional explosion, our processing time still took about 9 hours on a 25-node Hadoop cluster. So this was a huge amount of time to be pre-processing data. And we kind of realized that we were going about this problem all wrong. And like using a key value store wasn't the correct solution. So around mid-2011-ish, we kind of looked around at other solutions in this space to see if anything else could solve our pain. And there was nothing really out there that could. So it was really around this time we started talking about maybe we should build our own thing. And we looked at the lessons that we learned with using relational databases and using NoSQL key value stores. And what we found was the problem with relational databases was basically the scans tended to be somewhat slow. The problem that we saw with the NoSQL key value stores was the pre-computation time just took too long. And we kind of decided maybe it's not too hard to solve the problem that we saw with relational databases. So around mid-2011, we started really building out this system called Druid. And Druid is called Druid because the lead architect of Druid played a lot of World of Warcraft. So this is tribute. This is our logo for Druid. It's somewhat of a work in progress right now. So Druid is a distributed column-oriented data store. And if you're familiar at all with distributed column-oriented data stores, they basically architecturally are all somewhat similar. And each sort of distributed column-oriented data store does a few things particularly well. So in the example of Dremel, it does like Google's Dremel. It does ingestion of like arbitrarily nested data fairly well. In the case of like Google's Power Drill, it has some really cool compression algorithms. Druid is kind of designed to add numbers really, really quickly, and that's its like main value add. There's a few other things that I think it does pretty well. It allows for sort of arbitrary slicing and dicing of data, so you can filter your data really without any bounds. Druid is designed to be a production quality system, so it's designed to be highly available, and it's designed for an environment where failures are like an everyday occurrence as opposed to any sort of anomaly. And finally, Druid is this concept of real-time. And real-time is very much a buzzword, I think, in the data space nowadays. It's very much like big data or cloud. Like everyone says they're real-time, but it's like very unclear as to what that term actually means. For us in the Druid world, we consider real-time by two facets. One is really around the rate of query return. So when I ask my data store some question, how soon can I get an answer back? And we've kind of designed the system such that an answer can return in somewhere between 0 to 5 seconds. And we find that for most of our customers, that query latency is enough to provide them with an interactive experience. The other facet of real-time is around ingestion latency. And that is really around this idea of some event occurs. How fast can my data store actually ingest this event and then make it explorable? Typically, Druid can do this in somewhere order of about a second. Oftentimes, it's in the order of hundreds of milliseconds. But we find that interacting with our customers that they have a pretty interactive experience and they're pretty happy if they can see some event that has occurred in less than 10 seconds after it has occurred. So how does the architecture of Druid really allow for these like two facets of real time? I've been explaining the architecture of Druid in terms of a popular TV show in the 90s called Mighty Morphin Power Rangers. And the idea behind Mighty Morphin Power Rangers is whenever the good guys have to fight the bad guys, they summon these giant robots called Zords. And then these Zords come together and they form this giant fighting robot called a Megazord, which then like beats the bad guys and saves the day. And Druid architecturally is very similar. A Druid cluster is composed of many different types of nodes. And each of these nodes are really specialized to do certain things very well. And these different node types come together and they form a fully functional system that's designed to deal with your data problems. So there's a couple of node types that I want to talk about to kind of explain how Druid works. The first node type I want to talk about are real-time nodes. And real-time nodes kind of encapsulate the functionality to deal with the ingestion and querying of data streams. So basically, real-time nodes query data. They make queries available on data as soon as that data is ingested. And they do so by effectively buffering all your data in memory. And periodically, they take the data that they've buffered and they hand it off to some other node type to take care of. So it's this idea that real-time nodes always deal with recently incoming data. And once that data becomes somewhat outdated, it kind of hands it off and lets something else deal with it. What that something else is called are historical nodes. And historical nodes do exactly how they're named. They deal with more historical data. So data that real-time nodes have handed off are passed down to historical nodes. And historical nodes are like the main workhorses of a Druid cluster. They're kind of dumb, but they do a few things very well. Like they download data, and then they serve queries for that data. So they do like the parallel processing of queries. They do the distributed computation of queries. And they do like aggregates. In front of real-time and historical nodes, we have broker nodes. And broker nodes they encapsulate the functionality of basically knowing what data lives on what pieces of the cluster. So queries go through broker nodes, and broker nodes kind of figure out what real-time nodes or what historical nodes hold pieces of data that correlate to that query. And broker nodes forwards that query down to the historical nodes or to the real-time nodes. And then the real-time and historical nodes do their computation in parallel. And then they return the results to the broker, which does like the final level of merging and returns results to the caller. So broker nodes encapsulate this query scatter gather functionality. And they also support caching. OK, so storage. OK, so what does the data actually look like for Druid? Druid is designed to work with like transaction streams and time series data. So all your events always have this notion of a timestamp associated with it. And Druid requires a timestamp with every event. In this particular example, this can be the data that we ingest for Wikipedia, which I showed in that demo at the very beginning of this presentation. This data, it has a timestamp column with an indication of when the event occurred. It has like a page that was being edited. It has language, the city, the country of the person doing the editing. And it has things like the number of characters being added and the number of characters that are being deleted every time someone edited a page. So Druid stores data as columns. It is fundamentally a column store. And it is the reason why like, we can do aggregates and we can do like filters so fast. So what we do when we store columns is we take our page column, for example, and we utilize a method called dictionary encoding, where we convert every value that we see in the page column to some integer representation. So for example, this page column has two values, as Justin Bieber, has Kesha. We map the first ID, Justin Bieber, to 0. We map Kesha to an ID of 1. What we actually end up storing to represent this column is just a series of IDs. So here we can see that ID 0, Justin Bieber, appeared in the first 3 rows. Kesha appeared in the next 3 rows. Similarly, with our language column, we basically map the language English to an ID of 0. And we end up storing is just an array of zeros. So what's great about column stores and dictionary encoding is that this method lends itself very well to compression. When all you're doing is storing integers, the column becomes very easy to compress. There is a secondary index that we build. And this secondary index really allows us to do very fast filters on top of data. So what we actually do is for every single value that's within a column, we actually build a bitmap index for that value. And what do I mean by that? In our page column here, we have 2 values. We have Justin Bieber, we have Kesha. If we want to basically store a representation of all the rows of our data set that only contain the value Justin Bieber. In this case, Justin Bieber appears in rows 0, 1, and 2. So we can store some representation that indicates where this value appears. So we have basically this binary array where 1 indicates the value is there and 0 indicates it doesn't. So for Kesha, she appears in rows 3, 4, and 5. And what we end up storing to represent the rows that Kesha appears in is this array where we only mark the last 3 rows as being true. If you're familiar with like search engines at all, this method, all we're really doing right now is building inverted indexes. So why do we do this? Well, let's say if I issued some query and my filter was I only wanted to return those rows which contain Justin Bieber or Kesha. What we can do is we can look at the bitmap index associated with Justin Bieber, which in this particular case are the first 2 rows. And we can look at the bitmap indexes associated with Kesha, which in this case are the last 2 rows. And we just OR these two binary arrays together. And what we get is the set of rows which contain one value or the other. So the bitmap indexes, the inverted indexes, are a very fast way for us to determine, for us to narrow down our data set and only find those rows in our data set that match some specific criteria. The other cool thing about building bitmap indexes is basically all we have is binary arrays, and binary arrays are really easy to compress. So the compression method that we use is called concise. It's based off of the thesis work of a PhD student in Italy. And concise is really just a more efficient implementation of word-aligned hybrid, which itself is really just a variation of run length encoding. So we actually store our compressed bitmap indexes, and we never decompress for any queries. And what that lends itself to is using a lot less memory when queries are issued, and subsequently faster scan rates as well. Okay, so
sorry, quick question.
Yes.
Do you have a mechanism if you're supposed to do the dictionary encoding, or do you always?
We always dictionary encode. So both forms of like encoding that I've talked about is something that we always do for. So dictionary encoding is done really at a column level, and then the bitmap encoding, the bitmap indexes that I was talking about, are really done for like each value of the column. Okay, so in terms of availability, Druid is highly available, as I mentioned. So Druid supports replication. It supports configurable levels of replication. So if your data is more important, you replicate it more. And kind of a cool thing that comes out of replication is you lose a node, it's no big deal because your data is still available. And we use this to our advantage in order to do software updates, where basically you can take one node down at a time, you can update it, you can bring it back up. And you can do this for every node in your cluster. So you get into this idea of being able to do rolling updates without any downtime of data. Druid is designed to run on commodity hardware. So really, starting up a Druid node is just a matter of starting up a Java process. And then terminating a Druid node is just stopping a Java process. So really, for about 2 years now, we've taken like no downtime to do any software updates to Druid. Yeah.
Is that because most of your Druid clusters are okay with multiple versions running at the same time?
Yeah, so we use multi-version concurrency control. Actually, because we deal with like event streams, a lot of our data tends to be immutable. So all data on like a historical node, all data in a historical cluster is immutable. And if we do updates or deletes, we're basically rebuilding blocks of data for certain time ranges. And those blocks enter the system and obsolete like old blocks.
How about storage itself? Like if you change like your storage, the way that you actually store things on disk, would multiple versions of Druid interact well with each other?
Yeah, so like, oh.
Yeah. Sorry.
Right, so the question was around storage and what happens with multiple versions of Druid running together. Our releases are designed to be backwards compatible. So it is actually a very frequent case that we'll have like multiple versions of kind of Druid floating around in a cluster. And Druid needs to be able to support that and in order to do updates without taking any downtime. Yeah. OK. So right now, what we're working on is trying to release Druid 06 and getting a stable version of that out there. The idea behind Druid 06 is we're really trying to make Druid more as a platform. And we've been really working on the extensibility of Druid, this idea that anyone can build modules for Druid and basically just drop those modules onto the Druid platform and have things just work. So modules that we've seen like contributed fairly recently are around cardinality estimation. We've seen modules for approximate histograms and quantiles. And we also have like modules that we built ourselves in order to do approximate top K calculations. Similarly, we're looking at, like we've actually built data ingestion modules. So we do batch processing and batch data ingestion through Hadoop. and we do this idea of like real-time processing using Storm. And with Druid 06, it should be pretty easy for anyone to really build their own module. If you want to build like proprietary modules that you want to keep internal to your company and not share with the world, that's something that's possible as well. So this final point here is Druid does have this notion of different node types, and we kind of want to make it easier for people to build their own node types from different modules that already exist out there. So if you have some problem that we haven't seen before, hopefully it shouldn't be so hard to build your own node type to solve that problem.
What languages does your API support right now?
So Druid is right now written entirely in Java. And the modules to extend Druid are also right now need to be in Java. We've seen contributions of ways of querying Druid that have been written in other languages, because the query interface is really just like an HTTP interface. So people have written like a Python library, an R if you're familiar with like statistics. And then there's been a little bit of work on like a SQL adapter, but that's not like very mature yet. Right. So it's really our hope to turn Druid more into a platform. And what we actually have sort of in production right now is we have batch ingestion that's being done through Hadoop, then that kind of just hooks up with Druid. We have streaming ingestion or streaming ETL that's being done with Storm that kind of hooks into Druid as well. And then we have these different components that build on top of Druid. So we have approximate algorithms that we've been experimenting with. And this is like approximate quantiles, approximate histograms, cardinality estimates, approximate top Ks. We have visualization components, similar to that dashboard that you guys saw a little bit earlier. And then we also have machine learning components. And I have a question mark on it because we only have one machine learning component right now. We do robust PCA to do trend detection. But it would be really nice if people would contribute more machine learning to Druid. That's something I'm always really interested in. Okay, so in terms of the Druid community, we were open sourced in October of 2012, so almost exactly 1 year ago. We have a growing community right now. We have around 30 contributors. Not everyone is like public right now, and they come from a variety of different companies. Druid is in production at several companies already. There's more information on our website. But it's always our hope to get more people interested in Druid and more people into production. Our support right now is mainly through the community forums and through IRCs. And we really love contributions. So contributions anyway, whether through docs or like answering questions or code itself, that makes us super happy. Okay, so finally some benchmarks. We've benchmarked our real-time ingestion on real-world data from anywhere between about 10 to 100,000 records per second per node. Ingestion rates very much vary with data complexity, but for the data sets that we've seen from people, these are some numbers. In one of our partner clusters, this is actually deployed at Netflix right now. They ingest at a rate about 150,000 events per second, and that's about 7 billion events per day. And that amounts to about 500 megs a second, or 2 terabytes of data per hour.
Is that on AWS or this Netflix?
Yeah, this is Netflix. They have their own internal deployment. Yeah.
Do you know what the nodes is at?
I want to say 15, but I'm not entirely sure.
Do you know what the cardinality of the data is and how many dimensions you're talking about?
I don't know the exact numbers. The cardinalities, like the highest cardinalities that we've seen are typically in the order of millions. Or, yeah.
So to tack on to that question
Yeah.
of cardinality, you don't handle something like floats, for example, as
Would-
a data type. I can imagine a column of floating point numbers being
Right.
very high cardinality.
Right. Typically, like Druid has different column types, and float columns is actually one of them. We typically treat float columns as more of a metric, which is like something we're going to aggregate over, versus a dimension, which may be something that we might want to like filter over. So the code is in place and to be able to support like different column types, but It's a matter of like the use case of those different column types. Does that make sense? Yeah.
When your cardinality has like millions of
Yeah.
elements, do you build a bitmap index for each one of
Yes.
them?
Yes. But there are, like our sharding scheme is we always shard first on time. And then we usually do like secondary shards based on like the cardinality of a dimension. So if you have an extremely high cardinality dimension, then we typically would build like several different shards for that dimension.
And so do you have the indices inside each time segment?
Yes.
Okay.
Yeah. So each segment will always have a set of like inverted indices associated with it. So it depends on this idea if you're treating the column as something that you want to explore or treating the column as something you want to aggregate.
So if I have an event that happened just once for like a particular user,
Yeah.
But I have 2 years of data,
Yeah.
I want to filter on that user, do I have to hit every single historical segment? Or is there another type of index that says you only need to look at this segment?
So sorry, could you repeat the question again?
Yeah, if you have a user that only appeared in one of your segments, but you don't know in which one,
Yes.
but you have a lot of segments, like 2 years of data,
Yes.
And you want to filter for this user, are you going to be querying every single segment?
Yes. So you're actually querying every single segment, but the merge of the inverted indexes should be something that should be very fast because almost every segment would just have like no information about that user. Yep. So actually I have a benchmark related to your question. The scan speed, the last time we benchmarked it, was about 33 million rows per second per core. And then our index compression, we found that using this concise compression method, our concise sets are about 70% smaller than just using straight up binary arrays. We can do an OR operation over about 1 million dimension values in somewhere around 5 seconds. So in your particular use case where you're scanning potentially several thousand segments, an OR operation over several thousand segments should complete relatively fast. Okay, so some takeaways. So Druid, I think it's very good for interactive, fast exploration over large amounts of data. And Druid is a good choice if you want analytics and not just like a straight up key value store. Druid is useful if you want to be able to do analytics on your data as it's occurring in real time. And if you want your system to be somewhat highly available, so you don't want any downtime. And Druid is fairly useful if you want to be able to have extensibility and flexibility with your data store. Some things that Druid may not be good for are if your data is so small that it fits into MySQL, then like MySQL is pretty awesome, and there may not be a reason to use Druid. It might be overkill. If you're kind of querying for individual entries or doing lookups, so if you're searching for a single specific thing, then perhaps Druid may not be like the ideal case. And Druid, because Druid mainly deals with append-only like event-style data, it's not particularly good at doing like updates or deletes. So if you have like OLTP-style transactions where you do a lot of updates and deletes, then Druid might not be the ideal solution. And if you don't really care about real-time ingestion or you don't really care about downtime at all, then there may potentially be other solutions out there as well. So as a final note, as I mentioned, Druid is open source. So if you're interested, our website is druid.io. We have a Twitter handle as well. I'm like learning a lot about how to use Twitter. So we do have a lot of information about events that we're attending and like recent updates and stuff on our Twitter feed. If you have any questions, we have our RC channel. Some of us basically just camp out there and just answer questions that the community has. OK, well, thank you all for listening. And I'd be happy to take some questions if anyone has any. Yes?
The first nodes that it writes to with the recent data, is it actually being stored there durably?
Yes. So I actually.
Repeat the question for the recording.
Oh, I'm sorry. So the question was around the durability of real-time ingestion, and specifically how durable is the real-time storage nodes that we use, right? So durability with real-time ingestion is done partially by the nodes themselves and partially by a message bus that we use to do like real-time ingestion. And for us, the message bus that we use is Apache Kafka. So the idea behind Apache Kafka is it actually acts like a buffer for incoming events. And within this buffer, you can have multiple nodes like read from the same buffer. So if you have like two real-time nodes reading from the same buffer, reading the same set of events, then you get replication of events across two nodes. What Apache Kafka also allows you to do is it allows you to reread events from some offset. So for example, if your node goes down and it comes back like a few minutes later, then you can basically check like the last offset that it committed and then reread events from that offset. The Druid nodes themselves also handle, they also have features that are built in to do like higher availability. But like we could perhaps talk offline about like the architecture there because it's a little bit more complicated. Okay, cool. Any other questions? Yes.
So no downtime due to software upgrades?
Yes.
Any downtime due to other reasons? What are they?
So the number one reason, so the question was there's no downtime for software upgrades, but what other reasons do we have for downtime? The number one reason that we've experienced downtime is because we run on AWS. And if AWS has an outage, then we will be affected. We've been working on a feature such that we can replicate data across multiple data centers. So we're thinking of basically having some of our data in AWS and then some of our data in like our own data center. And the idea is that if AWS goes down or if our own data center goes down, it doesn't impact us. Yeah, so Druid is designed to have no single point of failure, but if like half our cluster gets wiped out by an AWS outage, then that becomes a problem for us. Yeah.
You mentioned the caching on the broker node.
Yes.
Is that just caching the result for a whole query, or does it cache the results of the sub pieces?
Yeah, so the question was around how Druid caches queries. And Druid actually caches queries based on the fundamental like unit of storage that it understands, which are called segments. So it always caches queries on a per segment level. So it's not a query cache. It's a cache for like the data pieces that are accessed as part of a query. Sorry, I think there's another question.
Yeah. So it looks like Druid is basically a nice system around Kafka, Storm, and Hadoop, right?
Yes.
And so my next point would be, how do you compare with Hummingbird? And so we have to explain.
Right. So I'm not an expert on Hummingbird. I only know it at a very high level. And I think there's probably people that are better suited to answer this question than I am. And unfortunately, they're not here right now. My understanding of Hummingbird, it's more like data flow control for Storm. And whereas for Druid, it's more as like a persistent storage for processing that's done in Storm. So how we use Storm is we use Storm to do things like lookups, and we use it for doing things like joins. And when those operations are complete, that data then gets fed into Druid, and then Druid just acts as the store for that data. So Druid right now, it has a real-time ingestion component, but all data that's ingested by Druid all has to be denormalized. So like Druid has no support for joins. So we require like something like Storm to do that. So I can see a solution to be for like real-time ingestion to be like Hummingbird plus Storm plus Druid, something like that. Cool. Oh, one more question.
Perhaps you could tell us more about how the nodes that store the data layout and how they're synchronized. You mentioned no point of failure.
Right. So the question was around synchronization of the nodes that store data. We use Zookeeper to do sort of like all intra-cluster communication. And I didn't show it in the diagram, but there's basically another node type. It's called the coordinator node or a master node. And that node is really responsible for telling like historical nodes what data to load and what data to drop. Because the data that we deal with, at least on the historical cluster, are always like immutable, then we get around like problems like reconsistency because we're always dealing with immutable data. So the idea is like there's an explicit piece that does like coordination, and there's an explicit piece that does things like replication and distribution of data. And then the other pieces that are there, like the historical nodes, are mainly responsible for dealing with just queries and aggregates for those queries. Does that make sense?
Yeah, I think so.
OK, cool. Cool. Thanks. Thanks, guys.